So, welcome to Sundar's lecture. This is lecture number 52, and in this lecture, we are going to take a numerical example for Norton's theorem. By applying Norton's theorem, we are going to solve this particular problem. So, last class we have seen what is Norton's theorem, and we have also derived the expression to find what is the load current in a particular resistor if a linear network is given to us. And that linear network we have converted into the Norton's equivalent circuit. And we know how to find our ISC and ZTH. That is what we are going to apply in this particular network. See, this is point A and point B, and we have seen that this should be Z. We have assumed it to be Z, so it will be Z. And what is the Z here? It will be 4 ohms. And you need to find what is the current here. That is nothing but it will be IL. See, that is the given question. Find current through RL by Norton's theorem. And we are assuming that it to be IL. So this is the linear network. Inside the linear network, we have told that there will be some current source, voltage sources, and we have only one voltage source and two resistors are present inside the linear network. Now you see, by seeing this network, you just draw the Norton's equivalent network. So what is Norton's equivalent network? We have seen that it will be ISC that should be connected across a resistor or impedance, and that impedance, see, this will be ISC and this will be ZTH and this will be Z, and what is this one? This should be IL, current through the resistor, and this value is given here. What is that one? This is 4 ohms is given, right? And what is the formula? We have already seen. IL will be is equal to ISC into ZTH by ZTH plus Z, right? So we know this formula too. So now you need to find, we know what is Z, that is not an issue, and we need to find what is ISC and ZTH. So first what we do, we try to find ISC. So how will you find ISC? See, how will you find ISC? See, ISC, this linear network has to be kept as it is, and you need to short circuit this resistor, load resistor. And that is what we have done here. So you try to understand. So what you need to do, you need to short circuit this resistor. So if you do that, what you will have? So this will be 24 volt source, and this will be a resistor, and this resistor has to be, sorry, I made a mistake. So here there will be another resistor, and this resistor will be connected like this. This is the linear network, and this will be short circuited. And you need to find what is the current here. See, this will be plus minus 24 volt, and this is 6 ohms, and this will be 4 ohms, and we need to find what is the ISC here, or we will call it as Norton's current. Maybe this is also, we have not told this, but this can be also Norton's current. This ISC can be also considered to be Norton's current. So this current you need to find. See, if it is a short circuited, then obviously this 4 ohms resistor is short circuited. There is nothing connected here, because always current takes the path where there is no resistor or low resistance path. This is low resistance path. Obviously this will be connected like this. So then what is this one? What is this ISC will be? ISC will be what? 24 divided by 6. So it is very simple to find. That is ISC will be 24 divided by 6, and that should be is equal to 4 amperes. So ISC will be is equal to 4 amperes. That is what we have found now. So we have found what is ISC now. So we know what is ISC. and we need to find what is ZTH. So how will you find ZTH? See, to find ZTH, you need to only impedance are present in this circuit. You need to short circuit the voltage source and open circuit the current source. That is what we need to find. So in the linear network, so across this AB, you need to find what is the impedance value, that is ZTH, and you need to short circuit this voltage source now. So how will the circuit diagram? So a point AB is here, and you need to short circuit this voltage source, and there is a resistor here, and there is another resistor here, and you need to find across this point, across this point. That is nothing but it will be ZTH. ZTH across this resistance or across this point A, point B. This is point A, point B. We need to find what is the equivalent impedances, or we will, here it is resistor, so we will call it as resistor. Now you see how these two resistors are connected. See, both ends are connected, both resistors, both ends are connected. So obviously these two resistors are connected in parallel, and if it is connected in parallel, so what is the impedance? That will be ZTH will be is equal to, so it has to be 6 plus 4, and it will be 6 into 4, right? And this is 24 divided by 10. So obviously it will be what? ZTH will be is equal to 2.4 ohms. So we have found ZTH also. Right? Now you can find what is IL. So IL should be is equal to, what is ISC? It is 4 amps into, what is ZTH? It is 2.4 divided by, what is ZTH again? It will be 2.4, and what is Z now? It is 4 ohms plus 4 ohms, and if you simplify this, the IL comes out to be 1.5 amperes. 1.5 amperes. So that's all. So we have found what is the current through this load resistance or load impedance. I try to understand. There are so many ways to find what is the current in this resistor. We know mesh current analysis, nodal voltage analysis, and so many methods. But why this method is preferred? Now you can draw the equivalent circuit. Maybe I will draw it again. Norton's equivalent circuit. Norton's equivalent circuit will be this way. There will be a current source that is connected across the Thevenin's impedance and load resistance. Right? This is the Thevenin's equivalent circuit, and this will be ISC, this will be ZTH, and this will be Z. Right? What is the current flows here? That should be IL, and we know that these two values. Now what is this one? This is 4 amperes and this is 2.4 ohms, right? But this circuit has 4 ohms, and this is nothing but we have already found that is this is 1.5 amperes. Now you try to understand, this is the Norton's equivalent circuit. One thing, if I change this resistance now from 4 ohms to 6 ohms, and what is the current through IL? I need to find what is the current through this load resistance. If I change this to 4 to 6 ohms, how will you find this one? If you found IL by mesh current or nodal voltage analysis method, you have to solve the circuit again to get the current value here. That is the difficult thing if you are going by mesh current or nodal voltage analysis method. So So you just need to change this 4 ohms to 6 ohms. So what you do, you don't, it is not necessary to find the current through this branch again. What I have told you, if it is a mesh current or a nodal voltage analysis method, if this resistor is changed to 6 ohms, then you need to proceed from the beginning to find what is the current in this particular branch. But if it is a Norton's theorem, it is not at all necessary. See, we know what is the equivalent circuit now, and this 4 ohms we have changed it to 6 ohms, that's all. So now you see, if this Z will be is equal to 6 ohms, that's all. And you try to substitute in this formula, what you will get? See, IL will be is equal to ISC, because we have not changed anything inside this circuit. Inside between A and B, we have not changed this circuit. It is default circuit. So ISC will be 4 into, and ZTH, what is ZTH? We have found that it is 2.4 ohms divided by 2.4 plus 6 plus 6. Instead of this Z, here it is 4 ohms, here it will be 6 ohms. That's all. So if you simplify this IL will be is equal to 1.143 amperes. Try to understand. Try to understand. See, in a single step, we have found what is the current through this branch if it is a 6 ohms resistor. And it may be anything. And it may be anything. So this is the final value if Z is 6 ohms. So if Z is equal to 6 ohms. And if it is Z is equal to 8 ohms, just you change this to 8 ohms and find what is the current. It is very simple now. So if you have a electric circuit where a single resistance value will be changing, that depends upon time maybe. If you want to find what is the current in that particular branch every time, it is not necessary to solve the circuit again. We can easily find what is the current in that particular branch by using the Norton's equivalent circuit. That is the application of Norton's theorem. I think you would have understand what is the concept or what is the applications of Norton's theorem. Right? We will take up another problem in the next class and we try to solve that one. Maybe it is very simple problem. We have taken a simple problem to find what is the current in the load resistance. Maybe we will take a different problem, maybe a complicated problem in the next class, and we will solve those problems. Thank you.